Hanaa Assil, and today we're talking about organic chemistry and we're doing chirality. So this is for unit 4 of the A2 chemistry syllabus. So let us talk about chirality. What is chirality? It has to do with isomerism. Remember, in the O level and in the AS, we talked about isomers. And we said that isomers are two or more compounds having the same molecular formula but different structures. So they have the same number of carbons, same number of hydrogens, same number of oxygens, and so on, but they're arranged in different ways. So they have different structures. And we said these isomers could either be structural isomers or stereoisomers. So the structural isomers are the ones in which we have different chains or different positions of functional groups or different functional groups in the first place. So a chain isomer, for example, we said in the O level and in the AS that if we say we want to draw isomers of butane, now how do we draw butane? We know that butane is 4 carbons with 10 hydrogens. It is an alkane, so it has only single bonds. So I can draw all the 4 carbons after each other in a straight chain. Or I can draw it so that we have 3 of the carbons in a straight chain and 1 of the carbons is in the middle, which we call a branch. So in this case, these two are chain isomers of butane. If we say we want to draw isomers of pentane, also pent means 5 carbons with single bonds between them. Now these 5 carbons can either be in a straight chain, or we can have 4 and 1 branch, or we can have 3 in a chain and 2 branches. So these are all isomers of pentane. And we can also have positional isomers. That means if we're trying to draw isomers of an alcohol, you know that an alcohol should have an OH. So propanol, for example, I can either put the OH on one end or I can put the OH in the middle. So these are two isomers of propanol. Also, if we want to draw isomers of butene, we said bute is 4 carbons. Ene means I have a double bond somewhere. Now, the double bond can either be in the one end, either on this end or on the other end, or in the middle. So these are isomers of butene. You remember all of that from previous study. We can also have functional group isomers. That means if I have C2H6O, how am I going to arrange it? I can either arrange it so that it has an OH, so that's an alcohol, or I can arrange it so that the oxygen is in the middle, and that's a different functional group, which we call ether. Now, the stereoisomers we have also discussed before, and we said when we talk about stereoisomers, these are compounds with the same molecular formula, structural formula, but they have different arrangement of atoms in space. So they could be geometrical isomers or optical isomers. The geometrical isomers we did before also. We said geometrical isomers means I have a double bond somewhere. The double bond does not allow the groups to rotate around each other. So we say there is restricted rotation around the C double bond C. So if I have these two compounds, these two are exactly the same molecular formula and actually they have the same structural formula, but I can arrange them in different ways in space. So if the double bond is in the middle, I can have both CH3s on one side and the hydrogens on the other. So we call that a cis or a Z isomer. Now, the other one, I have the CH3s on opposite ends of the double bond and the hydrogens on opposite ends of the double bond. So we call that a trans or an E isomer. So these are geometrical isomers. So let's take a look at some of these questions to remind you about what we were saying. So if I have this compound, what is the name of this compound? Well, we said to name it, we first need to know what is the chain? Where is the chain? This is the chain. So it's something that has 4 carbons. So that is bute. How am I going to number them? Well, I number them so that the substituent, which is the iodo, should have a lower number. So actually this is bute-2-ene, and the iodo is on carbon number 2. So my answer is either A or C. Now, is it an E or a Z? Well, if you have the groups that are larger molecular mass on opposite ends of the double bond, that is a trans or an E. So that's the name of that compound. It's an E2-iodo-bute-2-ene. Now, what is chirality? Chirality means we're dealing with optical isomers. And an optical isomer is one that has a chiral center. Now, what's a chiral center? A chiral center is a carbon somewhere in the molecule that is bonded to 4 different groups. So it must be a carbon that has 4 different groups attached to it. Now, if I have something like compound A that we have, compound A has a carbon that is attached to a hydrogen, to a bromine, to a CH3, to a COOH. This carbon is a chiral center. Now, being a chiral center, that means I can draw a mirror image of this compound. So can you see the mirror image? So B is the mirror image of A. You imagine as if there is a mirror in the middle. So this is what they will look like. Now, actually, these two are different. They're not exactly the same. The mirror image is not superimposable on the first one. So you cannot bring B and put it on top of A and it will be exactly the same. It will not. The COOH will come on the CH3 and the CH3 will come on the COOH. So we say these are mirror images that are not superimposable on each other. Now, if I have an example of this, a compound that has a chiral center, meaning a carbon bonded to 4 different groups, and its mirror image is not superimposable on it, we call these two enantiomers. So enantiomers means a pair of chiral isomers that are non-superimposable mirror images of each other. So A and B are enantiomers. Now, if they are enantiomers, that means each one of them will have optical activity. Optical activity means the ability of the optical isomer to rotate the plane of polarized light. So if I have a light source somewhere, if I pass it through a plane polarized light, now this goes through a sample of an enantiomer, that means a sample of something that has a chiral center, then this enantiomer will rotate the plane of polarized light in a certain direction. Now, 2 enantiomers of the same compound will rotate the plane of polarized light in opposite directions. So if we go back to compounds A and B, we said these are enantiomers. And that means if I pass the polarized light through A, it will be rotated to one end. If it goes through B, it will be rotated to a different direction. So the 2 enantiomers rotate the plane of polarized light to an equal extent, but in opposite directions. That is, if they are individual. So I'm passing the light through enantiomer A, and then I pass the light through enantiomer B. Each of them will rotate the plane of polarized light equally, but in opposite directions. Now, if I have them both as a mixture, so I put the 2 enantiomers together, we call that a racemic mixture. So the racemic mixture contains both enantiomers. And that means one of them will rotate the light to one side and the other will rotate the light to the other side, and that means there will be no net effect on the polarized light. So if we have one enantiomer, it rotates the plane of polarized light. If I have a mixture of the 2 enantiomers, which are opposite to each other, then there will be no net effect on the polarized light. And the mixture of enantiomers is called a racemic mixture. Are we following? Okay, so let's take a look at some questions. He's saying which of these molecules can rotate the plane of polarized light? Well, we said in order to rotate the plane of polarized light, it has to have a chiral center. What's a chiral center? A carbon with 4 different groups. So we need to draw each of these. So let's draw A. If you draw A, this is what it looks like. Does it have a chiral center? Does it have a carbon that is attached to 4 different groups? It doesn't. That means it cannot rotate the plane of polarized light. Let's look at B. Does it have a chiral center? We said a chiral center is a carbon that has 4 different groups attached to it. No. Let's look at C. Does it have a chiral center? Well, if you look at this carbon, can you see this carbon? It's bonded to a chlorine and to a CH3, and then to a group on the right and to a different group on the left. This is a chiral center, so this will rotate the plane of polarized light. What about that last one? No chiral center, it will not rotate the plane of polarized light. Okay, let's take a look at this question. Which compound can show both geometric and optical isomerism? Do you remember which one is geometric and which one is optical? We said geometric means cis trans or EZ. And we said to have geometric isomerism, it must have a double bond in which the 2 carbons of the double bond, each of them is attached to 2 different groups. So that will give me a cis order trans. And of course, an optical isomer is the one that has a carbon bonded to 4 different groups. So let's look at A. Draw A out. This is how we draw A. If you sit down and draw it, this is A. The question is, it has a double bond, but will the double bond give you cis and trans? No, because on one end, it is bonded to 2 similar groups, CH3 and CH3. So actually, it will not give a geometric isomer. It does have a chiral center, so that carbon is bonded to a CH3 and an H and a group on the right and a different group on the left. So this one will give me an optical isomer, but not a geometric cis-trans isomer. What about this one? This one has the double bond with 2 carbons on the double bond. Each of them is bonded to a different group. So this will give me a geometric isomer. Now, will it give optical isomer? Yes, it actually has a chiral center in which the carbon is bonded to 4 different groups. So this is actually my answer. This will have geometric and optical isomers. What about the others? This one again will not give geometric, and actually it will not have optical because there is no chiral center. And this also, so my answer is B. Do we understand how to choose? Okay, this question says the compound this has a chiral carbon atom and exists as a pair of enantiomers. The enantiomers will have different what? Remember, when we draw these 2 enantiomers, these 2 are similar in everything except how it will rotate the plane polarized light. So these 2 compounds are exactly the same. They will give the same chemical reactions. They will have the same boiling temperatures. They will actually have the same color if they're supposed to be colored. But the only difference between them, because they have a chiral center, is they will rotate the plane of polarized light in opposite directions. Do we understand this? Please remember that enantiomers are the compounds that are mirror images of each other, and they have a chiral carbon atom, so the mirror images are not superimposable on each other. They will be similar in everything except the direction to which they will rotate the plane polarized light. Okay, this question says sucrose can be hydrolyzed by warming with dilute hydrochloric acid to form glucose and fructose. Circle or mark with an asterisk all the chiral centers. Again, Which one is a chiral center? We said it's the one that has 4 different groups attached to it. So where do we have chiral centers? Actually, all of these are chiral centers. All of these are bonded to 4 different groups if you look at each one. So all of these are chiral centers. Now, state the physical property associated with molecules which have chiral centers. We said if they have chiral centers, then they are optical isomers, and so they rotate the plane of polarized light in different directions or in opposite directions. What types of stereoisomerism can exist in molecules of the following substance? We said stereoisomers means either it will form cis strands, that is EZ, or it will have optical isomers if it has a carbon attached to 4 different groups. So first of all, will it give me EZ isomerism? Well, let's look at the double bond. The carbon on the right is bonded to 2 similar groups. It's bonded to 2 H's. So this will not give EZ isomerism. Now, will it give optical isomerism? Yes, because this carbon is chiral. It is attached to 4 different groups. So actually, what I have is optical isomers. Okay? Which of the carbon atoms marked with an asterisk is the chiral center? Well, chiral center means the carbon has to have 4 different groups attached to it. Well, let's look. Which of these? Well, only the C, the one in C, that asterisk is bonded to 4 different groups. If you look at the others, the carbon that has an asterisk on it is not bonded to 4 different groups. Which formula shows an E isomer that also contains a chiral carbon? Well, we said E isomer means what? E means trans, means the groups on both sides of the double bond have the higher molecular mass on the same side of the double bond. Are we following? Now, chiral means it should have a carbon attached to 4 different groups. So let's look at A. Is A an E or a Z? Well, A is a Z. It's a cis. Does it have a chiral carbon? Yes, but it is a Z, not an E, so that's not my answer. Now let's look at B. Is this an E or a Z? Yes, actually that's an E, which is trans, and it has a chiral carbon, so actually that's my answer. Now, if you choose an answer, please check that the others are not your answer. So let's look at C. C is a Z, no chiral carbon. D is an E, no chiral carbon, so my answer is B. Menthol has a number of medicinal uses. It can be extracted from the peppermint plant, and this is the structure of menthol. And he's saying how many chiral centers are in this molecule. Well, again, where do we have carbon attached to 4 different groups? Can you see that these are the chiral centers that we have? Each of these is bonded to 4 different groups, so we have 3 chiral centers. What type of stereoisomerism will be shown by this compound? Again, stereoisomers means geometric or optical, cis trans or chiral. Okay, so does it have a geometric isomer? Will it form cis trans? Well, yes, it will, because the 2 carbons on both sides of the double bond have different groups attached to them. But does it have optical? There is no carbon attached to 4 different groups, so this is only geometric. This compound, he's saying what type of isomerism again? Again, does it have optical? Does it have chiral centers? Will the double bond form geometric isomerism? First of all, the double bond is attached to 2 similar groups, so it will not form geometric. But I do have a chiral center, so that means this will form optical isomerism only. Which of these structures is not identical? Identical means exactly the same, and that means exactly the same isomer, whether we're talking about chiral or here, of course, this is just chiral centers. So which of these are not identical? If you look at A, B, and C, A, B, and C, if you look at A and rotate A as it is around each other, around itself, it will give B and it will give C. Can you see that? But D is actually a mirror image of A. Mirror image means it's a different enantiomer, so it's not identical. So A and D are mirror images. B and C is just if you take A and just turn it around that carbon, you get B and then you get C. Okay? This compound, he's saying, draw a circle around the chiral carbon atom on this structure. Where do we have a chiral carbon atom? Of course, you're expected to understand the skeletal structure, so you should realize that this one is the chiral carbon that has 4 different groups attached to it. Here he's saying these 2 compounds are EZ isomers. Explain how this type of isomerism arises. We said, why do we have EZ or cis strands? Due to restricted rotation around the double bond. The double bond does not allow the molecules to rotate around each other. Draw a circle around any part below that causes the EZ isomerism. Of course, we said EZ isomerism is if I have a double bond and the 2 carbons on the ends of the double bond are bonded to different groups. So, of course, this double bond causes the EZ isomerism. State the property associated with optical isomerism. We said if they are optical isomers, what do? They rotate the plane of polarized light in opposite directions. State the structural relationship between a pair of optical isomers. Use a label diagram to identify the structural feature that results in optical isomerism of one of these compounds. So if we say that we have these 2, what is it that makes them a pair of optical isomers? The fact that they contain a chiral carbon with 4 different groups attached to it, and they are non-superimposable images of each other, and we're supposed to draw these isomers and their mirror image. Lactic acid is produced in muscles as a result of anaerobic respiration. He says, give a reason why lactic acid shows optical isomerism. Again, we said optical isomerism because it has a chiral carbon attached to 4 different groups. A laboratory sample of lactic acid does not rotate the plane. Of course, we said if we have optical isomers, each of them should rotate the plane of polarized light. But if I have a sample of lactic acid that does not rotate the plane of polarized light, what does that mean? It means I have a racemic mixture. Do you remember what was a racemic mixture? It's equal amounts of the 2 enantiomers. So they will rotate the plane of polarized light in opposite directions, and that means they will cancel each other, and there will be no net rotation of the plane of polarized light. Okay, let's talk about SN1 and SN2 and the relationship to chiral compounds. If you remember, SN1 was a kind of nucleophilic substitution that occurs in the tertiary alkyl halides. Do you remember which ones are tertiary alkyl halides? If the carbon attached to the halide is attached to 3 different carbons or to 3 carbons. So tertiary alkyl halides, I have a carbon attached to bromine, and that carbon is attached to 3 carbons. So that's a tertiary. Now, we said if we are trying to do nucleophilic substitution, that means I want to remove the Br and put, for example, an OH. What is the mechanism that happens? We said for a tertiary alkyl halide, what happens is the Br breaks away first. So the electrons on the bond between the carbon and bromine will go to the Br and it will break away to form Br minus, leaving my alkyl halide with a carbocation. If you remember, the positive charge on the carbon was called the carbocation. Now, in a second step, the hydroxide ion will attack that carbocation to give me the alcohol. So this is how we changed alkyl halides to alcohol. Now, in this case, because the Br leaves, I end up with a carbocation. Now, this carbocation can be attacked by the hydroxide from either side. So we can say that the hydroxide ion attacks from the front or from the back. And that means if I'm starting with something that is chiral, I end up with a racemic mixture because I have equal chances of attacking from the front or from the back. So I will form the two mirror images that can be formed, and that means I will have a racemic mixture. And we said if I have a racemic mixture in which I have both enantiomers to equal amounts, then there will be no net effect on polarized light. Do we understand this? This is for the SN1. Now, if we're talking about SN2, we said SN2 happens where? If we have primary or secondary alkyl halides, and we said what happens is the hydroxide attacks directly at the carbon, so it will attack from the opposite side of the Br. And that means when I end up with an alcohol, I will end up with only one of the enantiomers because I'm coming in from a specific direction. So what happens is if this carbon were chiral, then I will end up with one specific enantiomer. So my product will rotate the plane of polarized light. Okay, let's take a look at these questions. First of all, which classes of halogenoalkane can react by SN2? We said SN2 reacts with primary or secondary alkyl halides or halogenoalkanes. The molecule shown has 3 functional groups. Which of the functional groups can undergo nucleophilic addition? Do you remember which of these does nucleophilic attack? Remember that if I have a carbonyl, which is Z, yes, I can have nucleophilic attack. And if I have a halogenoalkane, we just said we can have a nucleophilic attack. But remember that double bonds, like the one at Y, will not do nucleophilic. It does electrophilic reaction. Okay. A sample of bromoalkane contains a single optical isomer. It reacts with hydroxide ions in SN1. So from this, and the result is a racemic mixture. So from this information, you can deduce that RBR is likely to be what? We said which kind of alkane, bromoalkane, will do SN1. The one that does SN1 is a tertiary, and this is the one that results in a racemic mixture. So the products will not rotate the plane of polarized light. When a single enantiomer of 2-iodobutane reacts with sodium hydroxide, the product is a mixture of enantiomers. So if I have iodobutane, this is iodobutane, and we're attacking it with hydroxide, that means we're doing nucleophilic substitution. So this is what kind of alkyl halide? This is a secondary, right? So the secondary, he says, produces a mixture of enantiomers. That means that the reaction proceeds via a carbocation intermediate. Remember that the secondary can do SN1 and it can do SN2. When an optically active isomer of 2-chlorobutane reacts with hydroxide ions to form butanol by SN1, the product is not optically active. Why is that? We said SN1, the 2-chlorobutane forms a carbocation. This is planar about the positively charged carbon, so you can attack, the hydroxide can attack from either side. So what we end up with is a racemic mixture. Both enantiomers are possible, and we have overall no effect on the plane polarized light. Okay, I hope this was clear. Thank you for listening, and the next video will be on the next part of organic chemistry, so please keep listening. Thank you.